This video will give you an overview of spatial modeling, why we do it, why do we really care. The problem is we need to make better decisions, right? One of the things we'll talk about later in the semester is I'm really concerned about the decisions that we make being very short term. And by short term, I mean in the next year or two, 3 or 4 years. We're not making good decisions for humanity 100 years out. And I do believe that modeling can help with some of that. Also, the issues that we're looking to solve are growing larger spatially, like climate change. It impacts the entire Earth. Issues with the Pacific Ocean, huge spatial areas, and that's a real challenge. More complex data. I'm now working with salmon data, and they are really complicated. More data, just larger number of years, number of points. Typical that I'll work with million entry databases, so lots of data. How often these require special algorithms, and we'll talk a little bit about that. And we're also trying to meet the needs of much larger groups of people. In other words, instead of scientists just publishing something in a scientific journal that goes to other scientists, we really want to impact decision makers, the public, and involve them in what we're doing. So a lot of issues, a lot of challenges for us. These can't be solved with traditional GIS analysis and traditional approaches. We need to have new and different approaches. Also, ArcGIS just isn't going to be enough. ArcGIS has some modeling capabilities, but it doesn't manage complex data sets well, doesn't process large data sets, doesn't let us create custom models, or it does let us run batch processes, but you don't really want to use Model Builder. You want to learn Python for that. So the thing to do here is see ArcGIS as what it's good at. It's a GIS package. It's good at doing common GIS operations and some specialized things, and at making maps. So we need other solutions to be able to solve these problems. R is one that we'll explore a lot in this class because it's a very powerful statistical modeling tool. We'll use Bluespray a little bit. Bluespray has its niche, as do a whole lot of other software packages. And you'll need to go find software packages in your area of discipline because there's probably specialized packages for model within your discipline, modeling within your discipline, sorry. Okay, this is a little bit of an example of a marine spatial planning project that I worked on. To let you know, once you take this class, you tell people you're a modeler, you may end up, as I did, showing up in a room and everyone looking at you going, oh, Jim is the modeler who's going to review our work. And I was like, what? And this was 100 raster layers, millions of model runs, years of work using multiple modeling packages. Fortunately, I was familiar with Maxent and ArcGIS. I had never heard of Marxon, but I was with an expert in about a week, spending my evenings reading about what Marxon was. And what they were looking at is where to put marine protected areas along the Oregon coast. And so they broke up the coast, which is pretty long, came up with target best solutions, and they did this across a whole variety of parameters, and then used this Marxon product to put them all together to find a sum or a weighted, you could think of it as a weighted average of where the best places to put marine protected areas would be to avoid things like fisheries and commercial operations. So that's an example of a good sized one that I worked on. The data sets that we have can be really big. We have MODIS circling the Earth at 250 meters per pixel twice a day. Huge amount of data that is literally pouring down onto the internet for us to access. Landsat, I don't know why that says 30. It should now be over 40 years. Has the entire Earth at between 15 and 30 meters twice a month. DayMet is daily climate predictions. LiDAR point clouds can be huge, multiple gigabytes. And now we have UAVs or drones that can go out and you can collect a couple gigabytes in a day. So they are just little data generators at very high resolution. All right, so there's different ways to look at this data. The first one is the type of spatial data. Points, polygons, and polylines are the ones we've worked with for a long time, as well as rasters. First three, of course, being vector data. Those can have attributes or measures associated with them. They can be contiguous or categorical. They can be dates or descriptive text. So there's some variety with the attributes. And they can be remotely sensed, or they can be field data that someone on the ground collected. And of course, all of that is increasing, especially the remote sensing. Now we put those together and look at almost all spatial data. we find that everything's got some type of measure, maybe occurrence or height or something else, temperature, precipitation. All of it has some spatial coordinates and all of it has some temporal information. Even if the data doesn't have a date stamp on it, it was collected at some point in time and the world keeps changing. So that's something to remember with your data. Temporal things can come up and bite us in our models if we're not remembering that our data was collected at a specific point in time. And if that was 20 years ago, well, things in the ground may have changed a lot. Also, our data can be 2D, which is the most common, two-dimensional. It can be 3D or 4D or n dimensions. If you work in the ocean world, they like using n-dimensional data to represent not only the volume of the ocean, but time as well. So they very quickly move into 4-dimensional data and sometimes higher. Also, this data can have a relational or hierarchical structure to it, complex structure to relate the data back to itself. All of this is making our lives a little more challenging, but also the models more interesting. Another consideration is how the data is stored. Large files, and I'm talking large, I've seen people try to put together terabyte single files. This is a bad idea. You want to instead work with large sets of files, particularly with rasters, which I've done most of my work with. If you have a terabyte of rasters and each one of them is a few gig, that's okay. You can move that around in pieces. You can write code to move it. If you have one huge terabyte file, which I saw a project do, you can't do anything with it. You literally can't get it off the computer it was built for. Relational databases are one I work with quite a bit, but they're good for relational data and vector spatial data, not for rasters. Distributed data, more and more we're seeing data that's distributed across multiple computers, both for backup and also just to handle the size of it. The cloud is really what that is. Google has over 10,000 servers. Your data that's up in Google's cloud is actually scattered across a number of different servers. And then there's hierarchical storage, which I'll just mention briefly, is this idea that you have on your computer a relatively small amount of storage, but it's very close and very fast. The cloud has a huge amount of storage on it. No problem handling terabytes of data, but it's distant from you, so it's going to be slower to access. So that's the idea of hierarchical storage. Different levels to the storage with trade-offs in it. Now these are a little bit of my definitions. They aren't as formal as I'd like, but when I talk about spatial modeling, it's an abstraction of something spatial, typically on or near the Earth's surface. People do spatial modeling in the universe, at other planets, on the sun. Mostly we'll deal with the Earth. Both marine and terrestrial environments, but it's an abstraction. It's a generalization of something spatial. I separate that from spatial processing, where we're just converting spatial data for specific use. That would be something like projecting or otherwise transforming data for a use, say changing the file format, resampling it. Spatial analysis would be analysis that uses spatial data. So something like looking to see is there autocorrelation with a Moran's eye or running a linear regression. That would be spatial analysis, and that's merging into modeling as soon as we run something like linear regression, which is formally a model. And then there's simulation, which we'll talk about later in the semester, where we don't really have the data, but we're modeling something or simulating something that could occur often in the future. When we're looking at what we want to get out of modeling, the real goals is we want it to be very verifiable against the real world. In other words, we want to be able to go out and collect more data, bring it back, and show with that new data set that our model still works. So it should be something that represents the real world. It should be robust. That means that it should be repeatable. So we should be able to run our model over and over again with a little bit different data. We don't get wildly different results. We should also be able to play with the parameters and adjust them a little bit. And again, we don't get wildly different results. The methods are transparent, so you should be able to see them, like with linear regression, where you can just say y equals ax plus b. That's very simple. And we can show it to folks and explain it fairly easily. Not all our methods are that transparent. Okay, none of them are that transparent except for linear regression. Again, simple to understand would be nice. We want to be able to explain them. Often they are challenging to understand, even some of those that are really valuable. Should be applicable to real-world situations. So again, not only verifiable, but applicable. Climate change is a great example. It's a real-world situation that folks are modeling all over the world, trying to get a handle on. And of course, a lot of you are already dealing with real-world situations and real data. And the real world should be within uncertainty bounds of the prediction. So it's a little more abstract, but basically you want to make sure you have realistic results. Again, the example I use is when I see a linear model that predicts tree heights that are negative. That would not be a valid thing, right? It'd be outside of what we would expect even with uncertainty. One of the things I'll talk about, especially with Maxent, is overfitting the data. The graph in the upper left is one for tamarisk in the US in response to temperature, and that is its logistic output of its probability of presence. So chance that you would find it in an area that has that temperature. Now take a look at that graph and put on your natural resource hat and say, what physiological basis would you find inside of a plant that would explain a graph that is that complicated? Now, I'm not a botanist, so me and one of my colleagues, Dr. Greg Newman, we took this over to a botanist at Colorado State and said, does this make sense? When we first worked with Maxent, he looked at it and said, no, that doesn't make any sense whatsoever. There's nothing in a plant that would give us that level of complexity. In other words, that means the model is overfitting the data. And they'll do that to get better performance characteristics, because that's what models do. They try and optimize performance characteristics. It's up to us as modelers to look at that and say, well, wait a minute, we need to take that with a grain of salt and figure out how to simplify that model, even though that's going to make our performance look worse. And we'll talk more about that. The graph down in the lower right is much more realistic, and in fact, that's actually from a greenhouse experiment. So that's measured from plants. That's more what we would expect. Now, there are some general modeling methods, some of which you've seen. Density and interpolation are used commonly in GIS, and this is introducing one of the topics we'll talk about a fair bit, which is the conversion of data from one format to another. In other words, if you need to convert points to a density surface or a raster, we can use a density model where we take and sample the points, particularly the density of the points, and convert those into values inside of a raster. Interpolation takes points with measured values, temperature, precipitation, those kind of things, and creates a continuous surface. So those are modeling methods that you've probably either used, and I'm sure you have used data that was created using those modeling methods, even if they didn't tell you that. Correlation and regression is where we will spend most of our time in this class, and that's again where we're taking points with measured values and continuous covariates. We will do some categorical covariates, but mostly continuous. And from that, we get a continuous surface, which honestly can be then used as a covariate, also known as independent variable, in another model. And we can have hierarchical models, which we'll talk about. Simulations are very general, and we'll talk about those just at the end. They get very specialized very quickly and usually require either a long time to learn the software package that supports them or to create your own. So here's an example of density. You might have a density of points, and you could create a model that shows where there is certain densities. Now, this is not a correlation with anything. It's just looking at the density of the points in space. A couple different methods for that are minimum convex polygon, which is very popular in wildlife, very simple, provides good results, and kernel density estimates, or KDE, is another one. Now, interpolation is a very important modeling method. Interpolation is a very important modeling method, and not necessarily that we're going to use it in this class, but because an awful lot of the data sets that we get, particularly our independent variables, were created using interpolation. So the climate data we get, all kinds of other things, soil maps, DEMS, were all at some point interpolation was used to create them. Now, we've mentioned autocorrelation briefly. This is a place where autocorrelation comes in. In order to be able to do interpolation on a point data set, that point data set needs to have autocorrelation. And actually, the environment needs to autocorrelate. In other words, for these points that was used to create this DEM, the values near this point need to be similar to the value that's at that point. So there needs to be a gradual transition between these points. If that's not the case, we can't do interpolation, doesn't have autocorrelation. So this modeling method relies upon autocorrelation. Usually autocorrelation is a bad thing for modeling. Here it's actually critical that it be there. And there are some examples we'll talk about where people have made interpolated surfaces where they didn't have autocorrelation, and so you really shouldn't be using them. Okay, these are different interpolation methods. Kriging, nearest neighbor, and inverse distance weighting tend to dominate. Kriging is the only one that's statistical and produces an error surface with it, so I tend to like it. Nearest neighbor you want to be careful with because it's good, but it doesn't produce statistics, although it doesn't generate new data. Inverse distance weighting looks very nice. It's nice and smooth, but it creates new values that weren't there before, so we tend to shy away from it. Instead, we'll tend to use Kriging or nearest neighbor to create layers to use in modeling or any statistical approach. Okay, correlation and regression. Again, this is where we'll focus for most of the class. This means we have some variable that's being predicted, and that is dependent upon other variables. So again, I've worked mostly with plants. Plants are dependent upon things like temperature, precipitation, to some extent based on the plant, to soil type, water saturation, those kind of things. So they're dependent upon those environmental variables, many of which we can get rasters for. And we'll look at habitat suitability, and then there's a whole bunch of other ones: fire, land use change, disease risk, productivity, etc. There's a whole bunch of different methods for doing correlation or dependence models. Systems of differential equations were very popular when I was in school. Fortunately for all of you, they've pretty much fallen out of favor because we have much more powerful tools available now that really work better with what natural resource systems do. Common statistical functions like linear regression are good. We'll also look at GLMs and GAMs. Bayesian inference is kind of new. It's pretty cool. We'll talk about it. Of course, we're going to do lots of regular regression. Trees, we'll look at categorical and regression trees. Neural nets were popular for a while. They seem to be dropping off. Oh, I should mention index models are kind of the old ones that were hand built. You see those once in a while, not very often. Graphical techniques, again, kind of fallen out of favor. We'll look at machine learning methods, specifically Maxent, and we'll talk some more about that. And nowadays, you're also seeing combinations of these. Combinations being put together, which is pretty cool to do, but we have to be careful about the complexity of our models. Now, one of the things that we are going to be doing is we're going to be doing a lot of nonlinear work. So we're going to break away from linear regression very quickly and never see it again during the course, because again, most natural resource systems do not respond linearly. Now, this is an example of Pearson's correlation coefficient, okay, that shows basically when you have a relationship, a correlation between variables, and this is important not only between your independent and dependent variable, but between your independent variables to see if they co-vary. And these are just some fun examples. Simulations. So when you can't get the data, when it's out in the future or something like a big disaster or fire that you really don't want to create to build your model and validate it, we'll tend to use simulations. And these are very popular, especially in climate, population models, disasters, fire modeling, and shipping. Folks like Amazon use these models all the time. And you can then create a simulation without having to actually do the experiment. Now, validation then becomes the issue. This is a really fun example, one of the earliest ones of cellular automatons. And we'll also mostly look at agent-based modeling because it's a very powerful one for things like disease spread and other things that involve higher level organisms. Some other examples of where spatial models are used: floodplains for disaster preparedness. FEMA is big on modeling. They do some very cool modeling. I work in habitat and species distribution modeling. Soil erosion, ice extents tied to climate models, especially nowadays. Oil spill extents, bark beetle infestation. These are all ones that I've had some level of experience with. Geologic layers and earthquake ruptures. I haven't been involved with that, but I've seen some very cool modeling on how earthquakes work. Flight control software and fire dynamics. And I've had some students work with the fire dynamics software, which is kind of fun. This is just a really cool model of atmospheric humidity. Okay, so some characteristics of models, some things about them. They can be stochastic or have a random component or deterministic. Most of what we will work with will be stochastic in nature. In other words, they have some random component, so we would expect our residuals to be non-zero. Deterministic means you just run it over and over again and you always get the same result. Not usually what happens with natural resource data. Transparent or black box. Transparent would be something like linear regression, where it's easy to look at the equation and see what's happening. black box would be like Maxent, where it's very difficult to see the math and to see what's really happening internally. So we do things like response curves to be able to see what's happening or get a picture of what's happening. They can be simple or complex, rigorous or lax. We want rigorous. We don't want them to be lax. In other words, rigorous would say that it has rigor to it. We run it over and over again. It produces the same result. We change parameters. It stays pretty much the same. Doesn't sort of float all over. Applied or theoretical, we're leaning towards applied, but there's some fun theoretical stuff that we can play with. Internal or external evaluation. Awful lot of internal evaluation being done nowadays, and that means that we're using the same data, basically the same data that was used to build the model, to test it. That has some real negatives to it. We would always love to build a model and then go out and collect whole new data, or really have someone else go out and collect whole new data sets and test our model against that. Against those new data sets. Then they can also be parametric or non-parametric, which we'll talk about again. There's a lot of software out there to do modeling. ArcGIS has some cool modeling stuff in it, particularly the geospatial analysis wizard. It's pretty neat for doing interpolation. R is really the one that has all the models, everything in it, keeps growing, goes crazy. But there's other ones out there, especially in specific disciplines like Maxent. NPMR, not using as much as I used to. Blue Spray, I've built. It has Hemi in it, some other tools. Envy and IDL being used in remote sensing. MarkSand I mentioned. WinBugs for Bayesian. BioClimb is actually a really cool old modeler. And there's other ones. I'm just going to jump through some of these. So simulations, that's one where we're going to struggle a little bit because I haven't found the perfect simulation software to use in this class. So we'll talk about that later. And in the end, you can always build your own models, which is really what I do. And some students I've worked with build their own models. Nothing wrong with that, except you do have to be able to program to do that. So looking at a very high level for what we're going to be doing, or when you're doing your modeling process, especially for your project, is we start with defining the problem. What's the problem we want to solve, or what's the model we want to build? What do we want to predict? Investigate the topic. So we can't do a natural resource model without going out and reading papers and reading reports and learning about the species and the environment that we're working in, because it's really easy to take a data set, create a model, and think that that model has some level of accuracy. And over again, I've seen people make mistakes, including myself, when we assumed the model was correct because we didn't know enough about the actual environment that the data came from and what was happening there. So we gather, process, and analyze the data. Many of you will go out in the field and gather your data and process and analyze it. I tend to get most of mine off the web. I just spent all summer and fall collecting data on salmon, processing it, and doing some analysis on it. Mostly gathering it and processing it, but all off the web. I didn't go out and get to see any salmon except for one trip. We investigate and select the methods for how to do the modeling. Then we find, evaluate, and select the software. And that can be really key, especially when you're looking at modeling packages in your discipline. You want to spend some time reading about what other people use, how they use it, download it, spend some time with it before you really dive in and commit to it. Because there's an awful lot of software out there that doesn't do what it intends or doesn't have the support or the documentation to be able to figure it out. So that can be a barrier. Then we get into building, parameterizing, or running our models. Woo, that's the fun stuff. That's where we get to run a lot of models, see what happens. And that can be a little frustrating when you first get started because a lot of times your results aren't what you want. That's okay. I've been doing this a while. We keep beating on it until we get something good. And we usually can get something good if we've got good data. Sometimes we have to change the modeling approach. That's okay. Then we evaluate the model. How good is it? And evaluate the results, or the model that came out of it, what the model is predicting. Along the way, remember to document the assumptions that you have, particularly any assumptions that you might be violating the list from linear regression. That's okay. Uncertainties in your data especially. And any problems that others have seen, where their data and modeling worked, where it didn't. And I'll just leave you with this, because one of the things that we're always looking for is not only good models, but simpler models. Okay, so Occam's razor says that all things being equal, okay, a simpler explanation is better than a more complex one. It's often easy for us as modelers and scientists to come up with very complex answers. It's really the simple answer that not only tends to be better for prediction, but also is, of course, easier to explain to a wide variety of folks.